like to start numerical analysis by talking about numbers. Wait a minute, numbers, isn't that really basic? Well, of course, it's relatively basic for math majors, but it's still a good thing to go over again. And if you haven't had real analysis, this will definitely help you for real analysis. What's a rational number? If somebody came up to you on the street, said, what's a rational number? What would you say? It can be expressed as an integer over another integer. A ratio, right, of two integers. What are integers? Whole numbers, 1, 2, 3, 4, 5, 6, etc. 0 a whole number? Well, depends. It's certainly an integer. Some people say it doesn't count as a whole number, or another word is natural number. How about negative whole numbers? -1, -2, -3. Those are all integers too. Is there any condition on the ratio that you have to avoid? Yeah, the denominator can't be 0. So rational numbers are those of the form a over b, where these two things, a and b, are integers, 1, 2, 3, 4, 5, 6, etc., or 0, or -1, -2, -3, etc. And you can't divide by 0. B can't be 0. What do we know about decimal expansion of rational numbers? They're either repeating or they end at some point. They truncate at some point, like 0.5, right? That truncates. Though truth be told, you can write 0.5 as 0.5000000 with the zeros going on forever, right? What's another way you can write 0.5, actually? There is another way. It starts 0.4. 9, 9, 9, 9, yeah, with the 9s going on forever. 0.49 repeating equals 0.5. What? Yes, that's true. What, is that really right? Yes, it is. I'm not going to explain why at the moment, although here's a little bit of intuition. If they were different, what's between them? You can't think of anything. So they got to be the same. Now, my son would say 0.4999 with the 9s repeating and then put a 5 at the end, but that's not allowed because you can't put anything at the end because it goes on forever. What's an irrational number then? It's got a very simple definition, actually.
Not irrational.
Anything that's not a rational number. What do we mean by anything? Any decimal that's not a rational number? I guess we could say that. So I guess that means it's any number whose decimal expansion doesn't truncate and doesn't repeat. It would have to go on forever and ever without a repeating pattern. Though it could still have a pattern. You could go 0.01, 0.00, okay, 0.01, 001, 0001, 00001. I keep adding one more 0 every time. That would have a pattern, but it's not a truly repeating pattern. But that would represent an irrational number. What's a real number? Every number, every rational and irrational combined. Take the union of those two sets. That would be the real number system. All decimals, you could say. What's a complex number? Maybe I should have said what's an imaginary number first. A number that's not a real number. Do such numbers exist? Yes, they do. Why? I, the imaginary unit, has the property that I squared equals -1. What? When you square a number, you can't get a negative number. We can if we decide we want to. Is that allowed? As long as you make the number system consistent, it's certainly allowed. We can create the number system effectively. Or are we discovering it? As long as you make the complex numbers, call it C, which are numbers of the form a plus b times I, where I squared equals -1, and a and b are real numbers. So this is the set of all expressions of this form, such that a and b are real numbers where I is this imaginary unit whose square is -1. You call this the complex number system, and it truly does define a good number system that satisfies what's called the field properties of number systems. It is a field. If you're going to take abstract algebra right now, you will learn about fields in much more depth. It's got all the properties you'd want. Associativity, distributive property. Every non-zero complex number has a multiplicative inverse even. You can raise it to the -1 power. It satisfies consistent properties that you would want a number system to have. The only real question is, why do it? Is it useful? And that's the amazing thing, is that it actually is useful. Talk to somebody who's taking quantum mechanics and you'll find out how useful it is. Next two are a little bit more subtle. What's an algebraic number? Heard of that before? And its cousin, a transcendental number, or maybe I should say its enemy instead of its cousin. Algebraic numbers are those numbers that solve simple polynomial equations effectively. You got a polynomial, and even just keep the coefficients of the polynomial integers. It's got to satisfy such an equation. Transcendental numbers are those that are not algebraic. They do not satisfy a simple polynomial equation. So what's the nature of square root of 2? You think it's, well, first of all, is it rational or irrational? Turns out to be irrational, and that takes proof. Actually, the proof that the square root of 2 is irrational, I think, is the most beautiful proof in the universe. Not the most beautiful equation, right? That's e to the I pi plus 1 equals 0. But the proof that square root of 2 is irrational is, in my opinion, the most beautiful proof there is. And maybe we'll do it next Tuesday. So it's irrational. Do you think it's algebraic or transcendental? You're right. Hang on a minute. It's algebraic. What's a simple polynomial equation square root of 2 satisfies? X squared minus 2 equals 0. Right? X squared equals 2. Square root of 2 satisfies that. It's algebraic, not transcendental. What about pi? Rational or irrational? It's irrational. So that's much more difficult to prove, actually. The proof that the square root of 2 is irrational was done over 2,000 years ago by the Pythagoreans, and somebody got killed for it, the story goes. They were really mad at him and threw him overboard. The proof that pi is irrational was only done in the 1800s. It's much harder to prove. People suspected it, but it was much harder to prove that pi is irrational. Is it algebraic or transcendental? Do you think it solves a polynomial equation with integer coefficients? Doesn't seem like it would. And it doesn't. You can prove it's transcendental. That's also very difficult to prove and wasn't proven until after it was proven that it was irrational. So in the later 1800s. So we want to introduce these ideas because numbers form the foundation for numerical analysis, right? Lots of our solutions to equations will often be irrational numbers. Maybe sometimes even transcendental numbers if it's a transcendental equation, which can happen, like cosine of x equals x. You know, what's the solution of that equation? It's probably a transcendental number. Could it be algebraic? I suppose it could be, but I don't know if anybody's proven that that equation only has a transcendental solution, but it probably is transcendental. Usually exact solutions are irrational and maybe often transcendental, but we still need to approximate them. And we approximate them with decimal expansions, which are by nature rational. So we're coming up with rational approximations to irrational and transcendental numbers. By the way, before we go on, it's probably good to draw a little picture here just to give you a little feel for how everything is situated. You know, the complex numbers in this context form the biggest set. So you can pretend that's C. You could pretend that entire thing is the complex plane if you wanted to. And if you did, you'd only draw a line for the real numbers, but for the sake of just drawing a Venn diagram kind of thing, let's make the real numbers bigger. This would be the real numbers sitting inside the complex numbers. Every real number is a complex number, like 5 could be thought of as 5 plus 0i. So every real number is a complex number. Of course, the rationals sit inside the reals. The rationals are labeled with a Q for quotient. Where do the algebraic numbers sit inside here? Well, every rational is algebraic, but there are irrational numbers that are transcendental. So the algebraic numbers are somewhere in between here. Do the algebraic numbers have a symbol? Not that I've seen consistently, but maybe we can use a fancy looking A for algebraic. The irrationals would be everything in R that's not in Q. So everything in this upside down L shape would be irrationals. The transcendental is everything in R that's not in A, not in the algebraic numbers. So the skinnier upside down L shape would be the transcendentals. Okay, good to think about. Let's talk about solving basic equations. Linear equations. Start out really simple, right? Each equation has a unique exact solution. Why do I have exact in quotes? If it's in the form ax plus b equals 0, subtract b from both sides, then divide both sides by a. Of course, you can do as long as you're not dividing by 0. Why do I have exact in quotes? To tell you the truth, I forgot. Why do I have exact in quotes? Well, I suppose you could say it's possible for a and b to be irrational, like square root of 2. And you could write that answer as a ratio, but it would no longer be a rational number. Like if a were 1 and b were square root of 2, x would be negative square root of 2, which would not be rational. And yes, that's an exact expression representing the answer, but it's not, it's a symbol. It's not a decimal expansion. But it is unique. There's only one solution to such an equation. Yeah, what do I mean by exact? Okay, I was forgetting what I meant when I wrote that. Is the solution always irrational numbers? That is it always an element of the set of rational numbers Q? Well, the answer is it depends. It depends on whether a and b are integers, rationals, or possibly even irrational numbers. Nothing that says a and b couldn't be irrational numbers here, square root of 2 or pi. They could be. And then if they were, this would then possibly be no longer a rational number. Though usually for most applications, a and b are integers even. So in that case, the solution would be a rational number. Your turn, solve that equation. You all, as being mostly math majors, okay, it's a race. Who can solve it quickest? Okay, you can race against me. Zach, what'd you get? Uh-oh. Did I make a mistake?
No, I must do it wrong.
Well, I made a mistake.
No, I know what I did wrong.
Anybody get a weird fraction? Yeah, I got 23 over 11.
Yeah, that's I forgot if I was 12.
23 over 11. That's what I got. So you went ahead and just use the distributive property. It's a linear equation, isolate x on one side. Can always check it back in the original equation. We won't take the time to do that. As long as you don't make a mistake, you'll get a unique solution. All right, well, let's move on to quadratic equations. Again, I have exact in quotes because, okay, I think I was thinking putting exact in quotes because they're, in general, they're symbolic solutions instead of numerical approximations. As long as you get your quadratic in standard form, ax squared plus bx plus c equals 0. quadratic formula is what to use, right? As long as a is not 0. What if a were 0? Then you wouldn't even have a quadratic equation, so why bother, right? A better not be 0, otherwise it wouldn't even be quadratic. So good old quadratic formula is what to use there in general, though in special cases, you can often get away with factoring. That's nice if you can, but you got to use the quadratic formula in general. Yeah, by exact, that's an exact symbolic expression, but most people do like to approximate those things with technology. There often is a need for approximation, though sometimes you remember from the past, you get square roots that are nice. Square root of 25 is 5, for example, and your answers simplify to either a rational number or an integer. But in general, they will be, well, real, but not necessarily rational, right? They could be irrational. You could get a square root of 2 or something in there. So we need to numerically approximate them if we're going to be able to communicate those kind of findings to somebody who doesn't know much about square roots and stuff. Okay, your turn. Solve that one. Does that look right to people? Oh, and I didn't even notice it. Square root of 121. That's a perfect square, right? 11 squared. I didn't mean for that to happen. Negative 9 plus 11 is 2. 2 over 4 is 1/2. Negative 9 minus 11 is negative 20. Negative 20 over 4 is negative 5. People get that? Did I make a mistake? Looks like those are your two solutions, and they both happen to be rational numbers in this case, though that was just a chance. I didn't try for that to happen. Usually when we think about solutions of equations, we're thinking about them as equations of something equals 0. And so graphically, we're after where does the graph cross the horizontal axis? But the original equation wasn't something equals 0. It was two functions, two different functions, say, equaling each other, two quadratics whose graphs are two different parabolas. And we're after the x values where those intersect, right? Let's see, this first one, the one on the right there has a graph that's going to look about like this. Vertex at x equals 1. Right, when x is 1, this is 0. This other one, let's see, y-intercept of -3. It's going to look something like this for the other one, skinnier. That must be 1/2 right there. And they must intersect way over here somewhere at x equals -5. Somewhere up there, they intersect. Okay. I just picked that example randomly, and it turned out they had rational solutions. I wasn't expecting it. But kind of nice that it happened. All right, what's the next step up in difficulty? Linear to quadratic to cubic, quartic, quintic. You kidding? No, I'm not kidding. Exact solutions of cubics. Typically 3 of them. By the way, I said with quadratics it's typically 2. When would it not be 2 with a quadratic? When the thing under the square root is, yeah, you said it, multiplicity of 2. From the quadratic formula, the thing under the square root is 0. The plus or minus doesn't affect anything then. Plus or minus 0. And you get 1 repeated root. For a single quadratic, that's just when it touches the axis at one spot. Cubics, typically 3 solutions. What does it look like? Question mark, question mark, question mark. Is there a formula? There actually is. And in fact, in senior seminar, we learn about it, sort of. Actually, in senior seminar, we learn about the solution of what are called depressed cubics. Cardano. Which I believe don't have an x squared term. And well, this formula that you see here is more complicated than the one we see in that class. I think Mathematica is making this harder than it needs to. But actually, you can solve in general even non-depressed cubics, and it gets even worse. Do you see why I did not write that down? There are three solutions here. Here's the first one right there. Here's the second solution right here. And here's the third solution right there. Whoa. Yeah, we don't want to write it down, but it does exist. It does exist. Have I ever taught it in a class before? Well, yeah, sort of in the senior seminar. I actually taught complex analysis before, and yes, I taught that method. It's better to teach it as a method, actually, rather than a formula. Teach it as a method. So we just asked Mathematica there. It is possible. Your turn. Solve that. I do want you to take 5 minutes to solve this one. Not using the formula, but you should be able to solve it without a formula, maybe with calculator help. Go ahead and work on that right now. All right, so what should you have done with your calculator? You should have plotted the function. Here's what the graph looks like when x goes between -4 and 4. Looks like roots are at -1, maybe 1/2, and 3. Though looks can be deceiving. How do you know for sure that those are roots? Quickest way I know to know for sure is, well, just to plug them in and see that you get 0. But a nice way to do that is with something called synthetic division. Some people know synthetic division and some don't. It's a shorter, more fun way to do long division. I think there's a root at -1. So what I'm going to do is I'm going to put a -1 right here. And then I'm going to put the coefficients that I see underneath this bar here, 2, -5, -4, and 3. By the way, if one of those terms was missing, like if there was no x term, I would want to make sure I put a 0 in there when you do synthetic division. Otherwise, it doesn't work. And the way you do synthetic division is you take the first number here, bring it down, put it there. Then you multiply these two numbers. -1 times 2 is -2. Put it right there. Add -5 plus -2 is -7. Put it right there. Multiply -1 times -7 is +7. Put it here. Add -4 plus 7 is +3. Multiply -1 times 3 is -3. Add 3 plus -3 is 0. Put a line there too. There's your remainder when you divide this polynomial by x plus 1. This is the remainder when, let's call this polynomial f of x. When f of x is divided not by x minus 1, but by x plus 1, because -1 is a root of x plus 1, not x minus 1. And the numbers that are left, 2, -7, 3, are the coefficients of the quadratic that you get as the quotient when you use that division. So what I'm trying to say here is f of x, by what we've just done here, can be written as x plus 1 times, look at these numbers as coefficients, 2x squared. It's a 2x squared, in case you can't see that well. Minus 7x plus 3. Take these numbers as the coefficients of the quadratic. To check it, you'd have to multiply this out. I'm assuming I haven't made a mistake here. If we had gotten a non-zero remainder, then when we divide by that thing, you'd have a plus whatever that remainder is here. And -1 would not be a root of this, but it is 0, so it is a root. -1 is a root of this polynomial. We can continue. We also thought 1/2 was a root. We can do synthetic division with a 1/2 here. Put the 1/2 here. Bring the 2 down. Multiply 1/2 times 2 is 1. Add -7 plus 1 is -6. Multiply 1/2 times -6 is -3. Add 3 plus -3 is 0. We get another remainder of 0. meaning we can continue this factorization as careful here. I put a fraction there, 1/2, so it would be x minus 1/2. We're not used to having fractions in our factorizations, but this would be correct. And then what's left is a linear polynomial with these coefficients, 2x minus 6. And there would be a complete factorization, though it's not the most common way to write it. A more common way to write it would be to factor a 2 out of this one, like this, and then distribute the 2 through there, right? X plus 1 times 2x minus 1 times x minus 3. That would be a more common way to write it. And it also confirms 3 is a root as well, as we guessed. So some cubics, we don't have to use the cubic formula. We can just solve because we're lucky, because there are rational roots. There's something called the rational roots theorem even that says if there are rational roots, there's a limited number of roots that are possibilities. Now, there may be no rational roots. That's the typical case, actually. Most cubics do not have rational roots. But special cubics that you make ahead of time for tests, future teachers, do have rational roots. And it's worth teaching still for the purposes of illustrating synthetic division, long division, and these ideas here. The ideas about factoring still work, but you could be dealing with irrational numbers here, like square root of 2 or cube root of 2 for that matter, or some weird combination of things when you do the factoring. But theoretically, it's always possible. Does anybody know what the theorem is called that says theoretical factoring is always possible, even though you might not actually be able to do it? It's got an important sounding name, starting with the word fundamental. Fundamental theorem of factoring, you could call it that. The more official name is fundamental theorem of algebra. Fundamental theorem of algebra says factoring is always theoretically possible, even if you can't actually do it. Isn't that a weird thing to think about? And the famous mathematician Gauss was the first person who proved the fundamental theorem of algebra. Factoring is always theoretically possible, even for a million-degree polynomial. A million-degree polynomial can be proved would have a million roots. Many of them could be complex numbers, and some of them could be repeated. But if you count all the multiplicities and count complex numbers, a millionth degree polynomial is going to have a million roots. You can prove that with the fundamental theorem of algebra. That's pretty amazing. Nobody would ever want to find them, right? I don't want to find the roots of a millionth degree polynomial unless it was a really simple millionth degree polynomial, like x to the million equals 2 or something. But it's theoretically possible. You want to graph a millionth degree polynomial? I don't think so. How about a fourth degree? Is it possible? Here's a general fourth degree. Mathematica, can you do it? Yes, look at that. Whoa. It goes on and on for quite a ways. And typically there are 4 solutions. Here's the first one. Where does it end? I'm not quite sure. It's not letting me scroll. Oh. There's the first one. That's the first root of a general fourth degree polynomial. There's a second, third, and fourth one. Whoa, what about a fifth degree? What about a quintic? According to Galois, no. What's Mathematica doing? Root. 1, 2, 3, 4, 5. Yeah, Mathematica is saying can't do it, sorry. Is that because it's so complicated that if Mathematica did it, it would take up more space in Mathematica than there is space in the universe? No, it's because it's actually not possible. And somebody actually proved it's not possible. Galois, spelled Galois. Galois, you know, it's French. Galois. Actually, Abel evidently proved it as well. You don't say Abel, say Abel. Galois was French. Abel was Norwegian, I believe. Anyway, they both independently proved fifth degrees cannot be solved. Quintics cannot be solved in general, though particular ones sometimes can. Like teacher created ones that have rational roots kind of. Isn't this fun? We're having fun. And you also can't solve sixth degree in general. Hextics. Sixth degree. Seventh degree, what would that be? Septics. That's a great name, septics. Eighth degree, octics. Ninth degree, I'm not sure. 10th degree, dodectics. Whatever their names are, you can't solve them in general. Symbolically, but this is really important. There still are solutions, right? That's what Gauss said. Could be complex numbers, could be irrational numbers. They still exist. You just can't find them exactly. You have to numerically approximate them. Punchline. Numerical analysis. Numerical approximations. In general, numerical approximations of solutions can be done even when exact answers are not available. Such quote-unquote solutions are called numerical solutions, though oxymoronically, they are not actually true solutions. They don't solve the equations exactly because they're decimal approximations. They are finite decimals, which means they're rational numbers, really. And most solutions are not rational numbers. Arbitrary equations, fifth degree and higher, say, it's going to be very rare unless they're teacher created that they're going to have rational solutions. So the true solutions are irrational numbers whose decimal expansions go on forever and ever without a repeating pattern. So we're only approximating them. So they're not really solutions. They're just good enough for engineering, right? Good enough for all practical purposes. Build a bridge, send a spaceship to Mars. You know, what was it, 20 years ago? I don't remember if it was the US or Russia or somebody else sent a spaceship to Mars and it flew right past Mars because they did a bad calculation. I think they used the wrong units even. Their numerical solution was not good enough. Went right past, didn't go into orbit. Lost $10 million worth of spaceship there. Probably even more, 100 million. We call them numerical solutions, but keep in mind they're not true solutions. Here's an example. There's a cubic that, did I check this out of time? I believe has no rational number solutions. You can get calculator numerical solutions, Mathematica numerical solutions. Let's do that now. Calculator, 5x cubed minus 4x squared plus 7x plus 3. I picked these coefficients randomly, so unless I'm very unlucky, the solutions are not going to be rational numbers. Here's the graph. Looks like there's only one real solution, right? It's a cubic, and the inflection point is, well, there's no local max or local min. There is an inflection point. Looks like there's just one real solution. What is it approximately? We can go to the calculate menu and go to the 0. Give a left bound for your guess, give a right bound, and give a guess. Calculator is saying it's about negative 0.3365929. In Mathematica, in the PowerPoint, I say we could use FindRoot or solve or NSolve. Okay, let's use FindRoot first. That's in general the thing we're going to have to use in general is actually FindRoot. What was the function again? 5x cubed minus 4x squared plus 7x plus 3. If you use FindRoot, By the way, I don't know if you noticed this, you need double equal signs in Mathematica for solving equations. Don't do single equal signs, it messes everything up. Single equal signs are assignments, not equations. And you give it a guess in curly braces, say x is negative 0.3. There we go, negative 0.336593. Yep, that's the same as the calculator to that many decimal places. NSolve should solve it as well, and you don't have to give it an initial guess. However, NSolve approximates all the solutions, including the complex number ones. In general, however, NSolve doesn't work for general equations because NSolve first tries to solve it symbolically and then approximates it, whereas FindRoot just approximates it. Are those different things? NSolve solves it symbolically. Think quadratic formula or cubic formula or quartic formula. And then approximates the answer. It's an exact form, so to speak, and then approximates the answer. FindRoot is just a numerical approximation scheme. It doesn't try to find the exact answer. How can you find an approximation without finding the exact answer? There are ways. Newton's method. What about in Calc 1, maybe? Newton's method is one way. Does solve work here? Technically, it does because it's a cubic, although Mathematica has changed how it's been programmed in recent years. It still just approximates it, though with these funny square root symbols there. You don't take the square roots of these things. Technically speaking, since it's a cubic, exact answers are obtainable. I think if you put cubics here, it makes it exact. Oh, cubics arrow true. That's what I got to do. There are the exact answers in symbolic form. Not too pleasant looking. You don't have to memorize that. But cubics arrow true for a cubic will solve it exactly, even with numbers in the equation. We still got to do our proof. What's our proof? By the way, you can solve transcendental equations this way too, including with FindRoot. Well, especially in general with FindRoot. What's the approximate solution of the equation cosine of x equals x? You can't use the inverse cosine function to solve this symbolically, because if you try, you'll see you don't get anywhere. Turns out there is an exact a solution, and it's close to 0.7 if I recall correctly, 0.739085. But if you try to use NSolve, it doesn't work. Just gives up because it can't be solved symbolically first before that's approximated. You've got to use something like Newton's method instead, is the point. We still have a proof to do. We got 8 minutes left. Based on something called the Intermediate Value Theorem. The Intermediate Value Theorem, or IVT for short, guarantees the existence of roots of continuous functions that are not necessarily functions you're used to, but they do have to be continuous. Suppose, what's that? Oh, this is very symbolic here. Suppose f is a function, what's this mean? Whose domain is this closed interval from A to B, that's the domain, and whose codomain is the real numbers. There's the set of real numbers. So this is saying all my inputs are in this closed interval, and all my outputs are real numbers. This is standard notation. You'll see it in real analysis and abstract algebra. I use this kind of notation. There's your domain. I call that the codomain. I don't like calling it the range, because range means different things to different people in math. Doesn't mean this function is onto. Not every real number is an output necessarily. And in fact, if f is continuous as it is, it can't be onto here, turns out. Our book writes that assumption in this way. What's that? F, the function f is an element of this set. What's that set? This is standard notation for the set of all such functions, continuous, defined in the closed interval from A to B. F is an element of that set. F is a function that's continuous on the entire closed interval from A to B. That's the notation our textbook uses. K is any number between f of A and f of B. Then, if those hypotheses are satisfied, there exists a number C in the open interval from A to B such that f of C equals K. And how do we apply this? So, theorems are always very fancy looking. You can read that and say, okay, I guess I read it, but I have no idea what it means. You want to think about what it means. And this theorem, in the big scheme of things, is not too hard to understand. It's helpful to draw a picture to help you understand it. Continuous function means you can draw it without picking up your writing utensil, right? Maybe A is here and B is there. This function could be really wild, but it's going to be continuous. You can draw it without picking up your writing utensil. F of A is this number right there. F of B is this number right here. If K is any number between f of A and f of B, maybe right here, the theorem says there's a number C between A and B so that f of C equals K. In this case, with this picture, there's more than one such C. There's one right about here. There's another one right about here. One right here. One right here. And one right here. Looks like there's 5 values of C. I could call them C1, C2, C3, C4, and C5, such that f of C equals K. Theorem just says there's at least one. That's all you care about, typically. Oftentimes, K is taken to be 0, which means you're after the x-intercepts if K is 0. And for this function, there's 1, 2, 3, 4 x-intercepts, 4 roots of the function. And what you want to do is you want to then use this theorem to prove that certain equations have solutions. Let's do that real quick. Prove this equation, cosine of x equals x, has a solution. We saw Mathematica say it's about 0.7 something. Proof. Let f of x equal cosine of x minus x. Why am I doing cosine of x minus x? Yeah, where this equals 0 is going to be where that has a solution, right? This having a solution, a value of x where these are equal, is the same as this function having a root, f of x equals 0. Note that f is continuous for all x on the real number system. Also note that f of 0 is cosine of 0 minus 0 is 1 minus 0 is 1. And f of, let's use what? I want to use a number involving pi. How about pi over 2? Cosine of pi over 2 minus pi over 2 is 0 minus pi over 2 is negative pi over 2. 1 is positive, negative pi over 2 is negative. Then, if capital K equals 0, the intermediate value theorem can be applied to f on the interval from 0 to pi over 2. A is 0, B is pi over 2, to conclude that there exists, backwards E means there exists, a number C between 0 and pi over 2, such that, ST means such that f of C equals 0. i.e. cosine of C minus C equals 0, i.e. cosine of C equals C. Done. QED or praise the Lord, PTL. Okay, I know I did that very fast. That's because we were running out of time. Seems very wordy to do something really actually kind of simple, but you should be wordy at least this much wordiness when you first do these kinds of proofs. You should acknowledge where your function is continuous. What is f of A? What is f of B? What is K? And say, okay, by the IVT applied to that function on this interval, we can conclude there's a root. That's how you apply or use the theorem.